morning, Manandal. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about one of the topic in electromagnetic waves and transmission lines as transmission line equation, followed by the secondary parameter of a transmission line called characteristic impedance. So before going to derive the equation for this characteristic impedance, first let me introduce about this transmission line equations first, right? So in order to write the mathematical equation for this transmission line, we will consider one simple lumped circuit element. So what it consists of lumped circuit elements means basically it consisting of four primary constants or primary parameters of a transmission line as R, L, G and C. Resistance, inductance, conductance and capacitance. Now in this, the input voltage is given by V and the output voltage is to be obtained as V plus delta V, where delta V is considered to be a change in output voltage. And the input current is represented with I and the output current is denoted with I plus delta I. And two series elements which are connected in the circuit or lumped circuit are given by here inductance L and the resistance as R. And the conductance G and the capacitance C are connected in shunt of this lumped network, where V and V plus delta V are respectively input voltage and output voltages of this transmission line lumped circuit elements. And I and I plus delta I are denoted by the input current and followed by output currents of this lumped circuit elements. Now consider here an infinitesimally means infinitely small section of the transmission line of the length delta x. Means we are representing all these fundamental parameters of this transmission line equation in order to write. We will consider all the fundamental primary constants with R into delta x, L into delta x, G into delta x along with C into delta x, where delta x be the length of the transmission line and it is represented very small. Hence we are denoted with a small delta and length will be given for x. Okay, and in order to write all these primary constants which are there in the circuit, first consider series resistance of the infinitesimal small section that is represented with R into delta x. See, series resistance that is represented with R and the length of that will be given with delta x. Similarly, the inductance is also connected in the series, hence it is represented series inductance of the infinitely small section and it is denoted with L into delta x. And the two conductance and the capacitance two are connected in shunt in the circuit, hence two will be represented as shunt capacitance of the infinitesimal section that is C into delta x and shunt conductance of the section is given by C in G into delta x. Okay, so these are the four components which are there in the lumped element section of this transmission line with the length delta x. From this circuit, we are going to derive the mathematical equation for transmission line. Then here first, let the time harmonic voltage of a angular frequency omega. Means if the length we have considered for the transmission line means there must be changes in the frequencies along with the amplitudes. Now here let the harmonic voltage of an angular frequency that is represented with omega be applied at the input of the above lumped element. Lumped element section means resistance and inductance are connected in the series, whereas conductance and the capacitance are two connected in the shunt manner, where input voltage as Vi or let it be V and output voltages are denoted with V plus delta V and here it will be R, L, G, C and input current is denoted with I, and the output current is written as I plus delta I, right? So depending upon this lumped section, we are considering harmonic voltage of angular frequency omega be applied at the input of the lumped element section, and I be the current flowing through that circuit, right? As there will be drop in the series elements, means if any element is connected in the circuit, just if depending upon the connection there exists voltage drop or the dissipation in that particular element, we are supposed to consider. So as there will be drop in the series elements, means resistor R and the inductance L are connected in the series, means there must be some voltage drop in those two respective elements, and the output voltage of the above lumped elements along with the input and output may also going to change. So the output voltage will not be same as that of the input voltage. Why? Because series elements are there, means some input voltage must be drop in the respective two elements. Hence, input voltage and output voltage will not be same across that two lumped section elements. Similarly, some part of the input current will be bypassed. Means two conductance G and the capacitance C are connected in shunt, means in the parallel section case, current will be divided, hence input current is divided according to the connection, hence input current and output current also will not be exactly the same. So similarly, some part of the input current will be bypassed through the shunt capacitance and the shunt conductance. Hence, the output current will not be same as that of the input current, right? As the series elements or exist, means input voltage is not equal to the output voltage. Then because of this shunt connection, input current and output currents will not be the same. Okay, depending upon this principle, we are going to write here, let the current and voltage at the output be, means this is the output current and here it will be the output current, and V plus delta V is representing output voltage, right? Let the current and voltage at the outputs be I plus delta I and V plus delta V respectively. Then based upon that lumped element section, we are going to write the equations for input voltage and the input currents. So input voltage is equal to voltage drop across the series elements plus output voltage, right? Input voltage is equal to voltage drop across the series elements plus output voltage. Okay, depending upon this, input voltage notation from the circuit is V and output voltage notation as V plus delta V. This is Vi and this V naught, and this is given by drop across that series elements. And which two are connected in the series means resistor R and the inductance L. Hence, that is represented as R into delta X plus j omega L into delta X. Why? Because there are two reactive elements which are exist in the circuit, that is inductance L and the capacitance C. If two are exist, means we need to consider along with the reactive elements. Hence, R delta X plus j omega L into delta X into I plus V plus delta V. So this is nothing but according to the KVL, Kirchhoff voltage law, algebraic sum of entering currents is equal to leaving currents, or algebraic sum of the node voltages is same. According to the principle here, according to KVL, we will write the VI input voltage is equal to voltage drop across the series elements plus output voltage. So this is V, and here output is also represented with V. But in case of this series drops elements case, we have written R plus j omega L into delta X into I. Means this is nothing but V into, this is the drop, and it is represented with IR. Hence, according to Ohm's law, V equal to IR, we can write. Then based upon that, this is the equation has to be obtained. Now both sides, this delta V and this V and V gets cancelled. Now from that, delta V can be written as, means this is the term which is going to derive. Hence del V equal to minus of R into delta X plus j omega L into delta X, and here is the term which is to be multiplied as current I. Now consider this as equation number 1. So this is to be obtained from input voltage is equal to voltage drop across the series elements and output voltage. Similarly, input current is equal to now bypassed current through shunt elements plus output current. So input current II and the output current is resembles with I0 and this is shunt components. So input current IA is equal to bypassed current through shunt elements and output current. So and it is to be replaced here. I is equal to bypassed current through shunt elements means which two are connected in shunt connection, conductance G and the capacitance C are connected in parallel. So bypassed current through the shunt elements means G into delta X plus J omega C into delta X can be written based upon this statement. And here I plus delta I is for output current. Now both sides, this I and this I gets cancelled. Now we are going to write the equation for delta I, and which is equal to minus of G into delta X plus J omega C into delta X into V. So here also we are writing the equations for I is equal to I1 plus I2 plus I3. Means algebraic sum of currents which are entering is equal to the leaving currents. Now depending upon that, I is equal to IA is equal to bypassed current through the shunt elements plus output current. And it is given by delta I is equal to minus of G into delta X plus J omega C into delta X into V. See here also one of the reactive element which is exist in the circuit is nothing but capacitance. Okay, so two reactive elements are exist in the circuit. Those two are inductance L and the capacitance C. Depending upon these two equations, number 1 and 2, now we are going to simplify. See del V equal to minus of R plus J omega L. Now if you take in that R delta X plus J omega L into delta X into I, we have written in the equation number 1. Now in between these two, if we take delta X as common, R plus J omega L into I, right? So depending upon that, del V equal to minus of R plus J omega L into delta X into I. Now from that, and from this is from equation number 1. Now from equation number 2, there also we have G into delta X plus J omega C into delta X into V is the equation from 2. Now if you take delta X as common, G plus J omega C into V is the resultant one, right? So that is obtained from equation number 2 as del I equal to minus of G plus J omega C into del X into V, right? Now from these two relations means from this equation, if you want to write del V by del X is the ratio which is equal to minus of R plus J omega L into I. Consider that as equation number 3. And from this equation, del I by del X is equal to minus of G plus J omega C into V. This is equation number 4, right? So for the validity of lumped analysis at all frequencies, the length of the section delta X must tend to 0, right? In order to simplify that equation, we just consider here according to the lumped section elements analysis, limit delta X tends to 0, del V by del X is equal to. See here already we have considered from equation number 3, del V by del X is equal to minus of R plus J omega L into I, right? Now limit delta X tends to 0, del V by del X is equal to minus of R plus J omega L into I. Okay. Now in this case, we just replace limit delta X tends to 0, del V by del X by dV by dx value, right? So dV by dx is equal to minus of R plus J omega L into I. So here this is the change. We just consider according to this one as per differentiation. Hence dV by dx is equal to minus of R plus J omega L into I. Now consider this as the continuation part of that equation as let it be number 5. Now next is similar to that voltage equation. Here also the current equation can be written as limit delta X tends to 0, delta I by delta X is equal to minus of G plus J omega C into V. Now, by changing this one with di by dx is equal to minus of g plus j omega c into v. Now, consider this as equation number 6. So, previously what we have dv by dx is equal to minus of r plus j omega l into I. This is equation number 5. Now, from equation number 6, that is di by dx equal to minus of g plus j omega c into v. Right? Now, from these two, equation number 5 and 6, we are going to consider here first. Consider equation number 5 and this equation, differentiating this equation number 5 with respect to the x. Already it is differentiating with respect to x. Now again we are differentiating that one with respect to the x term only. Then it becomes d square v by dx square. Means already dv by dx is there. Again we are considering differentiation on both sides. Hence it becomes dv by dx is equal to minus of r plus j omega l into di by dx. Or d by dx of dv by dx can be written as d square v by dx square equal to minus of r plus j omega l into di by dx. Okay. Now from this d square v by dx square equal to minus of r plus j omega l into what actually this one di by dx according to equation number 6 it is minus of g plus j omega c into v. Now if we substitute in place of this di by dx by minus of g plus j omega c into v, right? So which is equal to minus into minus becomes plus, then r plus j omega l into g plus j omega c. That is d square v by dx square equal to r plus j omega l into g plus j omega c. Right? So now then into v is also exist. So d square v by dx square equal to minus of r plus j omega l into di by dx. If you differentiating this equation number 5 with respect to x, then it becomes, now if you substitute di by dx by this equation minus of g plus j omega c into v, then it becomes r plus j omega l into g plus j omega c into v s. Then continuation part we will consider this as equation number 7. Now differentiating equation number 6 with respect to the x. So previously what we have consider equation number 5, then we have differentiated equation number 5 with respect to x, then d square v by dx square equal to, this is the equation we have got. Similarly, consider equation number 6, means this is the equation number 6. Let it be di by dx equal to minus of g plus j omega c into v. Now consider that equation number 6 and differentiating that one with respect to the x. Okay, then it becomes, means already we have that equation as di by, means d by dx of di by dx equal to minus of g plus j omega c into, already v is there. If you differentiating that one with respect to x, then it will become dv by dx, which is nothing but d by dx of di by dx, means d square I by dx square equal to minus of g plus j omega c into, according to equation number 5, means what is that equation number 5? dv by dx equal to minus of r plus j omega l into I. Now if we substitute in place of this dv by dx by minus of r plus j omega l into I, then it becomes, already negative is there, then it becomes positive, then r plus j omega l into I is left out, which is equal to d square I by dx square equal to r plus j omega l into g plus j omega c into I. Right? So that is equation number 8. See, here we have got from equation number 7 d square v by dx square equal to r plus j omega l into g plus j omega c into v, and From this, d square I by dx square equal to r plus j omega L into g plus j omega c into I. So consider this as equation number 8, right? So from 7 and 8, we can write here, see, let gamma square equal to. So where gamma is said to be propagation constant of this transmission line, and it can be considered as gamma equal to root over r plus j omega L into g plus j omega c, where R, L, G, C are the primary constants of a transmission line and omega be the angular frequency of that wave, right? So gamma equal to root over R plus j omega L into G plus j omega C. Now, if we take square on both sides, then gamma square becomes r plus j omega L into G plus j omega C, right? So now, if you substitute in the previous 7 and 8 equations, total term by gamma square. Here also total term by gamma square. Then from equation 7 and 8, we can write d square v by dx square equal to gamma square into v, and d square I by dx square equal to gamma square into I, or called transmission line equations, right? See, d square v by dx square equal to gamma square v, and d square I by dx square equal to gamma square I are known as transmission line equations with the order of second, right? So where gamma square is nothing but r plus j omega L into G plus j omega C, and gamma is said to be propagation constant of a transmission line, which constitute attenuation constant alpha and phase constant beta, right? So these two are called transmission line equations, or in another way we can write d square v by dx square minus gamma square v equal to 0, and d square I by dx square minus gamma square I equal to 0. These two are called transmission line equations. Voltage and current equations with order of 2, right? So from the above two relations, both the voltage and current are governed by the same differential equation with the second order, right? So this looks like second order differential equation with voltage and current relations. And these two are called transmission line equations. Okay. So to write the mathematical equation for this transmission line, we just consider first a simple lumped element section, which consisting of 4 primary constants of a transmission line, as include resistance, inductance, conductance, and the capacitance. Now based upon that, we have derived d square v by dx square minus gamma square v equal to 0, and d square I by dx square minus gamma square I equal to 0 are called transmission line equations, right? So if you solve the second order differential equation, so it looks like second order differential equation. Then if you find the solutions for this, then solutions are given by here, b equal to v plus into e power j omega t minus gamma x plus v minus into e power j omega t plus gamma x, and I equal to I plus into e power j omega t minus gamma x plus I minus into e power j omega t plus gamma x. The similar equations which we have already evaluated in the case of electromagnetic fields. Electromagnetic wave equation or uniform plane wave equation. There also we have got electric field intensity E is nothing but Em plus e power j omega t minus gamma x plus Em minus into e power j omega t minus plus gamma x. Similarly, H is equal to Hm plus into e power j omega t minus gamma x plus Hm minus into minus plus e power j omega t plus gamma x, right? In place of E and H, here we have voltage and currents. So this is the case we have assumed field theory. Now to write this voltage and current equations, we have considered circuit theory, right? This is the fundamental difference between this field theory and the circuit theory. right? Where voltage and current equations are to be obtained from the transmission line equations with the help of lumped section simplification, right? So V voltage equation with the amplitudes of forward traveling wave as V plus and backward traveling wave as V minus with the phase functions as j omega t minus gamma x and j omega t plus gamma x. Generally, we are assuming all the electric fields are aligned on the x direction. Their electric fields are deals with voltages, hence the resultant V will also be in terms of x direction. Right? Now, I equal to I plus e power j omega t minus gamma x plus I minus into e power j omega t plus gamma x, where gamma be the propagation constant and it is given by gamma equal to alpha plus j beta, where real term alpha is said to be attenuation constant and imaginary term beta is said to be phase constant. If you combine these two, alpha and j beta, which gives us the one of the constant, secondary constant of a transmission line called propagation constant gamma. Okay, so V and I are the two solutions for the second order differential equations of transmission line equations. Okay, so this is the way we have evaluated the transmission line equation from the a small section of a transmission line. Now, if you find in detail means if you substitute gamma by alpha plus j beta, right? As we know that propagation constant gamma, which constitute attenuation constant alpha and the phase constant beta, then V of x gamma t. See, that is not only varies with x, y and z, but also varies independent variable called time t. Then in order to express that equation, voltages and currents, we just write here V of x comma t, which is equal to V plus into e power minus alpha x e power j omega t minus beta x. Previously what we have, V equal to V plus e power j omega t minus gamma x plus V minus e power j omega t plus gamma x. If we substitute gamma by alpha plus j beta, then it becomes V equal to V plus e power j omega t minus of alpha plus j beta plus V minus into e power j omega t plus into x alpha plus j beta into x. Okay, so if you write this equation separately, V plus e power minus alpha x into e power j omega t minus beta x, j into omega t minus beta x plus V minus e power alpha x into e power j omega t plus beta x, right? So that's where here if you express gamma by alpha plus j beta, then V of x comma t equal to V plus e power minus alpha x into e power j omega t. If you take j as common between these two, means e power j omega t. So if you consider first the voltage equation, that is V of x comma t equal to V plus into e power minus alpha x into e power j omega t into e power minus beta x. Then if you take j as common, this becomes e power j into omega t minus beta x. And similarly here, the positive term means omega t plus beta x. In the similar way, if you want to write the equation for currents, that is I of x comma t equal to I plus e power minus alpha x into e power j into omega t minus beta x plus I minus into I power alpha x e power j into omega t plus beta x, where V plus I plus and V minus I minus are the arbitrary constants which are to be evaluated by using appropriate boundary conditions, right? So here, now to write the solutions for the mathematical equation of a transmission lines, now we have considered second order differential equation, and their propagation constant gamma is replaced by alpha plus j beta. Then the V of x comma t and I of x comma t voltage and current equations solutions are obtained as like this. Okay, so this is about transmission line equations. Now we are going to learn another topic in this particular lecture is characteristic impedance. Generally, it is denoted with Z0. Z is the notation for impedance. We are writing Z0 here. That is the notation for the characteristic impedance, one of the secondary parameter of a transmission line. There are two secondary parameters of a transmission lines. Those two are Z0 and gamma. Characteristic impedance as Z0 and propagation constant as gamma. These two are called secondary constants of a transmission line. So to derive here characteristic impedance equation, we just consider the differential equations of a voltage and currents equations from the lumbar section. So the voltage and current equations for transmission line are given by first dV by dx is equal to minus of r plus j omega L into I. This is written from the series elements which are connected in the circuit. And di by dx is equal to minus of g plus j omega c into V, and this can be written according to the shunt elements which are connected in the circuit. So R and L are connected in the series, where conductance G and the capacitance C are connected in shunt or parallel connections, right? So depending upon that, we have got dV by dx is equal to minus of r plus j omega L into I, and di by dx equal to minus of g plus j omega c into V. Okay, so consider these as 2R, 1 and 2 equations, and if you write the solutions for those two, then V equal to, right, after simplifying the second order differential equations, the solutions are given by here V equal to V plus into e power j omega t minus gamma x plus V minus e power j omega t plus gamma x, and I equal to I plus e power j omega t minus gamma x plus I minus into e power j omega t plus gamma x. These are the two solutions which we have got from the transmission line equations. So those two are d square V by dx square minus gamma square V equal to 0, and d square I by dx square minus gamma square I equal to 0. These two are called transmission line equations, which are the order of second. So if you find the solutions for those two, these two are obtained as I equal to and V equal to. Okay. So now from these two relations 1, 2 and 3 and 4, now we are going to write here. Then substitute equation number 3 and 4, means V and I solutions in equation number 1 and 2. So first consider here d by dx of, means first consider equation number 1. In that you just substitute equation number 3, right? Then d by dx of V is nothing but V plus e power j omega t minus gamma x plus V minus e power j omega t plus gamma x equal to minus of r plus j omega L into I, right? So I is nothing but here I plus e power j omega t minus gamma x plus I minus into e power j omega t plus gamma x, right? So if you substitute, if you consider first equation number 1, in that you just substitute 3 and 4, then this becomes d by dx of V plus into e power j omega t minus gamma x plus V minus e power j omega t plus gamma x, which is equal to minus of r plus j omega L into I, that is I plus e power j omega t minus gamma x plus I minus into e power j omega t plus gamma x, right? So upon simplifying this equation, means d by dx of first left side V plus e power j omega t minus gamma x plus V minus e power j omega t plus gamma x equal to minus of r plus j omega L into the total equation as I. Now if you differentiate this equation with respect to x, then V plus and V minus are constants. Now d by dx of e power x as first e power x, and we are considering with respect to x differentiation, means minus gamma as the resultant of differentiation. Then here also gamma is there, hence plus gamma. So minus gamma V plus e power j omega t minus gamma x plus gamma V minus e power j omega t plus gamma x, which is equal to minus of r plus j omega L into I plus e power j omega t minus gamma x plus I minus into e power j omega t plus gamma x. Right? Now both sides if we compare means in between these two if we take see both sides if we compare this e power j omega t minus gamma x as first and e power j omega t plus gamma x as separately, then we are going to get first. See minus gamma v plus e power j omega t minus gamma x equal to, on the RHS part, minus of r plus j omega l into I plus into e power j omega t minus gamma x. Now both sides if we compare the forward traveling waves and backward traveling waves separately. Now from forward traveling wave here minus gamma b plus e power j omega t minus gamma x equal to minus of r plus j omega l into I plus e power j omega t minus gamma x. Okay. Now if we compare the negative terms means gamma v minus e power j omega t plus gamma x equal to minus of r plus j omega l into I minus e power j omega t plus gamma x, right? So both sides if we compare these two, then e power j omega t minus gamma x, e power j omega t minus gamma x, and e power j omega t plus gamma x and e power j omega t plus gamma x gets cancelled. From those two relations, see, gamma v plus equal to, if we cancel those two, what is left out? Minus gamma v plus, and here minus and this minus gets cancelled. Gamma v plus equal to r plus j omega l into I plus is left out, right? So from those two, see, gamma v plus equal to r plus j omega l into I plus. Now v plus by I plus equal to r plus j omega l by gamma, right? So r plus j omega l by gamma. So previously we have considered this one gamma square. Let gamma square equal to, how we have written, r plus j omega l into g plus j omega c. Okay, r plus j omega l into g plus j omega c. So from this gamma equal to root over r plus j omega l into g plus j omega c. So from these two relations, v plus by I plus equal to r plus j omega l by gamma. If we substitute this gamma by this equation, then v plus by I plus equal to r plus j omega l by root over r plus j omega l into g plus j omega c. From this relation, see r plus j omega l by root over r plus j omega l into g plus j omega c. Now from this, if you take this r plus j omega l into inside the root, then it becomes r plus j omega l whole square by r plus j omega l into g plus j omega c. Right? So here, if you cancel means the square and root gets cancelled, this numerator term remains the previous. Okay? Then r plus j omega l whole square by r plus j omega l into g plus j omega c is left out. So this term and this term gets cancelled, which is equal to root over r plus j omega l by g plus j omega c as obtained. So that is given as like this. V plus by I plus equal to root over r plus j omega l by g plus j omega c. So voltage to the current is nothing but resistance, and here we are talking about impedance, then it is given by Z. Right? So similarly, if you consider the backward traveling waves. Backward traveling waves means previously what is that equation? Gamma v minus equal to e power j omega t plus gamma x equal to minus of r plus j omega l into I minus e power j omega t plus gamma x. Exponential terms both sides gets cancelled. Then what is left out here? V minus by I minus equal to minus of r plus j omega l by gamma is left out. See, we compare backward traveling waves. V minus by I minus equal to minus of r plus j omega l by gamma is left out. Right? So again, if you substitute gamma by this term, then minus of r plus j omega l whole square by the denominator part we have substituted r plus j omega l into G plus J omega C, right? So this and this gets cancelled, which is equal to minus of root over R plus J omega L by G plus J omega C. This is nothing but V minus by I minus equal to, right? So now based upon this, forward traveling wave and backward traveling wave means basically the transmission line equation solution consisting of two components. One is positive with respect to the direction and another one is negative with respect to that direction. So characteristic impedance Z0 can be defined as it is the ratio of voltage to the current and it is a function of the primary constants of a transmission line and operating frequency. And it is given by a notation for the characteristic impedance as Z0, which is equal to V plus by I plus equal to root over R plus J omega L by G plus J omega C. The parameters Z0 and gamma are secondary parameters of a transmission line, right? So previously we have learned the primary constants of a transmission line as R, L, G, C, resistance, inductance, conductance and the capacitance or primary constants of a transmission lines, and characteristic impedance Z0 and propagation constant gamma are called as secondary constants. Right? So depending upon this, the propagation constant gamma can be written as with the transmission line characteristics. These two can be written as gamma equal to R plus J omega L into G plus J omega C, and Z0 nothing but characteristic impedance is root over R plus J omega L by G plus J omega C. Right? So these two are called secondary constants of a transmission lines. So in general, the characteristic impedance Z0 can be defined as it is the ratio of voltage to the current in either of the directions, and it is a function of the primary constants of a transmission line and operating frequency. So what are the primary constants here? Resistance R, inductance L, conductance G and the capacitance C. So these four are called primary constants of a transmission lines, and along with omega is said to be operating frequency of a transmission line, right? So what we have learned in this particular lecture is from a small section of a transmission line, we have derived the transmission line equation, that is d square V by dx square minus gamma square V equal to 0 and d square I by dx square minus gamma square I equal to 0 are called transmission line equations, and characteristic impedance Z0 is called as secondary constant of a transmission line. Okay.
Like, share and subscribe. Hit the bell icon for more updates.